Increasing temperatures. Key messages. Increasing temperatures will likely increase electricity demand for cooling and decrease fuel oil and natural gas demand for heating. Thawing permafrost could damage oil and gas infrastructure and force changes to existing operations in Arctic Alaska, while decreasing sea ice could generate benefits for oil and gas exploration and production in Arctic Alaska. Increasing temperatures reduce transmission system efficiency and could decrease available transmission capacity, while more frequent and severe wildfires also increase the risk of physical damage to transmission infrastructure. Increasing air and water temperatures reduce the efficiency of thermoelectric power generation and could decrease available generation capacity. Recent trends and projections. Average temperatures across the United States have increased during the past 100 years, and the rate of warming has increased over the past several decades. Nearly the entire United States has experienced increased average temperatures, with the extent of warming varying by region, as illustrated by Figure 3. The warmest year since record-keeping began in 1895 for the contiguous United States was 2012, and the hottest month for the nation was July 2012. The average annual temperature for 2012 was 55.3 degrees Fahrenheit, 12.9 degrees centigrade, which was 3.2 degrees Fahrenheit, 1.7 degrees centigrade above the 20th century average. Higher average temperatures have been accompanied by the following impacts. Heat waves, a period of several weeks to weeks of abnormally hot weather, often with high humidity, have generally become more frequent and intense across the United States in the decades since 1960. High humidity and very high nighttime temperatures have characterized recent heat waves. Wildfire season has increased by nearly 80 days in the past 3 decades. The average duration of large fires has almost quadrupled from 7.5 days to 37 days, and the size of wildfires has also increased. Permafrost has thawed, and Alaskan Arctic sea ice cover has decreased. In September 2012, Arctic sea ice cover reached its lowest seasonal minimum extent in the satellite record, in other words, since 1979, reinforcing the long-term trend. The growing season has increased by about 2 weeks since the beginning of the 20th century. These trends are projected to continue. In the period 2021-2050, average annual temperatures across the United States are projected to increase by approximately 2.5 degrees Fahrenheit, 1.4 degrees centigrade, in a lower emissions scenario, and by 2.9 degrees Fahrenheit, 1.6 degrees centigrade, in a higher emissions scenario when compared to the climate of 1971-1999. By 2070-2099, temperatures are projected to increase by 4.8 degrees Fahrenheit, 2.7 degrees centigrade, under a lower emission scenario, and by 8 degrees Fahrenheit, 4.4 degrees centigrade, under a higher emissions scenario. In the United States, and conditions currently characterized as heat waves may become dominant summer conditions. There are seasonal differences in projected warming trends. Greater warming is projected in the summer and fall than in the winter and spring for most of the United States. Warmer temperatures are also expected to contribute to the following climate trends. Increase in frequency and intensity of heat waves. Increased frequency, intensity, and total acreage affected by wildfires in some parts of the United States, particularly Alaska, and parts of the West. Decrease average extent of sea ice in the Arctic by about 15% for every 2 degrees Fahrenheit, 1.1 degree centigrade of warming, with the possible disappearance of summer sea ice by the end of the century. Longer growing season throughout the United States. Implications for the energy sector. Increasing temperatures can affect key aspects of the energy supply chain. Higher temperatures that thaw permafrost can disrupt onshore oil and gas operations in Arctic Alaska. Higher temperatures also create a longer sea ice-free season in the Arctic, which can limit ice-based infrastructure, but allows a longer season for drilling. Increases in ambient air and water temperatures across the United States reduce thermal efficiencies of electricity generation from nuclear, coal, natural gas, concentrating solar power, CSP, bioenergy, and geothermal facilities, which can reduce available capacity and increase fuel consumption by power plants. Higher temperatures reduce the current carrying capacity and decrease the transmission efficiency of electricity lines. Finally, electricity demand for cooling increases when temperatures are higher, while demand for heating decreases. Oil and gas exploration and production. Oil and gas in Arctic Alaska are important sources of energy and are particularly vulnerable to climate change because temperatures in the Arctic are increasing twice as fast as the global average. The region contains an estimated 90 billion barrels of oil, 1,669 trillion cubic feet of natural gas, and 44 billion barrels of natural gas liquids, which amount to approximately 22% of the world's undiscovered oil and gas resources. Both onshore and offshore exploration and production have been and are projected to continue to be affected by increasing temperatures as permafrost thaws and sea ice continues to melt. Thawing permafrost could damage oil and gas infrastructure and force changes to existing operations in Arctic Alaska. As permafrost thaws, the tundra loses its weight-bearing capabilities. Risks to onshore fossil fuel development could include the loss of access roads built on permafrost, loss of the opportunity to establish new roads, problems due to frost heave and settlement of pipelines set on pilings or buried in permafrost, and reduced load-bearing capacity of buildings and structures. The Trans-Alaska Oil Pipeline was constructed with thousands of thermosiphons, or pipes that remove heat from permafrost, which may now be having problems caused by increasing temperatures. In addition, drilling wastes are typically disposed of using in-ground sumps that rely on the permafrost to prevent subsurface movement of the wastes into the surrounding environment. Thawing permafrost could require modifications to this practice or the adoption of alternative waste disposal methods. To protect the tundra, the Alaska Department of Natural Resources limits the amount of travel on the tundra, and over the past 30 years, the number of days when travel is permitted has dropped from more than 200 to 100, thereby reducing by half the number of days that oil and gas exploration and extraction equipment can be used. Decreasing sea ice could create other challenges for offshore oil and gas development in Arctic Alaska. The extent and thickness of Arctic sea ice has decreased by an average of 2.7% per decade and by more than 7% per decade in the summer according to satellite data going back to 1978. Reduced sea ice coverage could trigger new environmental regulations and protections for Arctic mammals, which may limit development opportunities. Reduced sea ice coverage limits ice-based infrastructure and transportation. Sea ice melting can also result in more icebergs, which may pose a risk to oil and gas operations in the Arctic because increased sea ice movement could interrupt drilling and damage rigs and vessels. Climate change may increase the frequency of polar storms in the years to come, further disrupting drilling, production, and transportation. Decreasing sea ice could generate benefits for offshore oil and gas exploration and production in Arctic Alaska. A longer sea ice-free season creates a longer exploration, production, and drilling season and may increase the rate at which new oil and gas fields are discovered. Warmer temperatures could open new shipping routes through the northwest and northeast passages and expand the spatial extent of Arctic exploration, a particularly noteworthy opportunity if the Alaskan and Canadian coastal shelf becomes permanently ice-free. The Arctic Climate Impact Assessment estimated that a reduction in Arctic sea ice could result in 90 to 100 navigable days per year by 2080, compared to the current 20 to 30 days per year, which would expand resource accessibility from sea routes. The combination of risks posed by warming and the opportunities gained through increased access to offshore resources makes it unclear whether oil and gas development in Arctic Alaska will be improved or hindered as temperatures rise. Thermoelectric power generation. Increases in ambient air and water temperatures are projected to reduce the thermal efficiencies of thermoelectric power plants. Reduced thermal efficiencies can result in reduced power output and additional fuel consumption. Because almost 90% of the electricity generated in the United States comes from thermoelectric power, such decreases in power output or increases in fuel consumption will hinder system flexibility or increase costs across the United States. Increasing air and water temperatures reduce the efficiency of thermoelectric power generation and could reduce available generation capacity. Natural gas, coal, nuclear, CSP, bioenergy, and geothermal power plants are all affected by elevated air temperatures. Warmer air and heat waves can increase ambient cooling water temperatures, which affects generation efficiency regardless of fuel source. For thermoelectric power plants, heat is used to produce high-pressure steam, which is expanded over a turbine to produce electricity. The driving force for the process is the phase change of the steam to a liquid following the turbine, from which arises the demand for cooling water. A vacuum is created in the condensation process that draws the steam over the turbine. This low pressure is critical to the thermodynamic efficiency of the process. Increased back pressure will lower the efficiency of the generation process. Increases in ambient air temperatures and cooling water temperatures will increase steam condensate temperatures and turbine back pressure, reducing power generation efficiency. The magnitude of the impact from increasing air and water temperatures on specific power plants will vary based on a number of plant and site-specific factors. For example, the power output of natural gas-fired combustion turbines, often used for peaking, is estimated to decrease by approximately 0.6 to 0.7% for a 1.8 Fahrenheit 1 degree centigrade increase in air temperature. For combined cycle power plants, output can decrease by approximately 0.3% to 0.5% for 1.8 degrees Fahrenheit 1 degree centigrade increase in air temperature. Plant output losses for combined cycle plants with dry cooling may be more sensitive to water-air temperatures, with reductions in plant output of approximately 0.7% for a 1.8 degree Fahrenheit 1 degree centigrade increase in air temperature. For nuclear power plants, output losses are estimated to be approximately 0.5% for a 1.8 degree Fahrenheit 1 degree centigrade increase in air temperature. While these studies project relatively small changes in percentage terms, when extended over the nation, they could have significant impacts on net electricity supplies if such losses in available capacity are not compensated by reduced demand or greater supplies elsewhere in the system when they are needed. When projected increases in air and water temperatures associated with climate change are combined with changes to water availability, electric generation capacity during the summer months may be significantly reduced. For example, the average summer capacity at thermoelectric power plants by mid-century is projected to decrease by between 4.4% and 16%, depending on climate scenario, water availability, and cooling system type, as compared to the end of the 20th century. Increasing water temperatures pose other risks to thermoelectric power plants and could reduce available generation capacity. Increasing water temperatures put power plants at risk of exceeding thermal discharge limits established to protect aquatic ecosystems and incurring financial penalties or forcing temporary curtailments. For example, during the heat waves that hit the Southeast in 2007, 2010, and 2011, the temperature of the Tennessee River exceeded 90 degrees Fahrenheit, 32.2 degrees centigrade. These increased water temperatures forced curtailment at once through cooling facilities along the river, such as the Browns Ferry nuclear plant, where cooling water discharge would have exceeded the thermal limit. During the 2007 heat wave, Duke Energy was forced to curtail operations at 2 coal-fired power plants. In 2012, several power plants across the country temporarily shut down or obtained special exemptions from their operating permits to exceed thermal discharge limits. Even if an individual power plant could safely continue to discharge its cooling water, the cumulative effect of multiple plants discharging high-temperature waters into a receiving body with already elevated temperatures may result in violation of environmental regulations. For example, multiple plants in the Ohio River Basin share the same water body. As this watershed becomes warmer, the cumulative impact of the energy system as a whole will likely need to be considered, not just the impact of an individual plant. In addition to the regulatory limits on thermal discharges from once-through cooling for power plants, several other factors influence the vulnerability of these power plants to higher water temperatures. These factors include the location of the water intake, depth and distance from shore, the location of the outlet, the fluid velocities of the inlet and outlet, screening mechanisms, Measures to reduce biofouling on heat exchanger surfaces, turbulence and pressure changes within the heat exchangers, and natural temperature distributions within the water column. For example, Unit 2 at the Millstone Nuclear Power Station was shut down in August 2012 after temperatures in Long Island Sound exceeded the maximum temperature at which the nuclear power plant is permitted to extract cooling water. However, Unit 3, which pulls water from deeper and cooler waters in the Sound, continued to operate. Renewable energy resources. In recent years, renewable electricity generation capacity in the United States has increased considerably. Despite the relatively small share of non-hydroelectric renewable resources in the current electricity generation portfolio, approximately 4%. About 30 states, including those with large energy markets such as California, have established renewable portfolio standards and other policies that will encourage higher penetration of these technologies in the future. Wind capacity increased from 2.6 gigawatts in 2000 to approximately 60 gigawatts in 2012, while solar capacity has also begun to grow rapidly. The potential impact of climate change will vary across renewable energy technologies and regions. Hydropower. Increasing temperatures could affect the operation of hydropower facilities and decrease available generation capacity in some regions. Increasing temperatures will increase evaporative water losses and consumptive water use in upstream watersheds, decreasing water availability for hydropower and the operational flexibility of hydropower projects. Increasing air and water temperatures may intensify stratification of some reservoirs behind dams and deplete dissolved oxygen, both in the reservoirs and downstream, which may degrade habitat for fish and other wildlife. Such water quality changes can affect growth, reproduction, migration, and survival of aquatic fauna and may cause changes in community structure and biodiversity. This may impel regulatory limits on hydropower flow releases to mitigate adverse ecological effects of water quality fluctuations. These limits can reduce the peak generation capacity of hydropower facilities and diminish the ability of hydropower facilities to respond quickly to electric system demands. Bioenergy and biofuel production. A longer growing season could increase bioenergy production, while increasing temperatures could decrease bioenergy production in some regions. Warmer temperatures lead to a longer growing season and could lead to gained acreage for multiple crops using land that otherwise could not be cultivated effectively. However, the overall effect of warmer temperatures on bioenergy production will vary by location, crop type, soil conditions, and producers' adaptive responses to the warmer temperatures, such as modifying their crop mix. For some crops and locations, increasing temperatures will increase evapotranspiration, ET, rates, thereby increasing water demand if increased water demand is not met by increased irrigation or precipitation. The increased ET rates could reduce average yields. Extreme heat could damage crops, and extended periods of drought could destroy entire yields. Such shortfalls may lead to increased price volatility in associated commodities. A recent study found that impacts from climate change could increase corn price volatility by a factor of more than 4 over the next 3 decades. Warmer temperatures and drought can also stress forests and make stands vulnerable to mortality from pest infestations, such as the pine beetle, which can reduce bioenergy production and increase fire risk. Wind energy. Changes in diurnal and seasonal wind patterns could influence future wind power resource potential as significantly as changes in average annual wind speeds. Projections of wind patterns vary by region, emissions scenario, and climate model. As a result, there is not yet consensus as to how a changing climate will ultimately affect wind resources in the United States. From an energy generation perspective, changes to wind speed and direction are important at a range of temporal scales, from annual averages to changes in diurnal patterns. Average annual wind speeds in the United States could decrease by 1% to 3% by mid-century, and by as much as 3 to 14% at times in the Northwest, according to a 2008 study. However, a more recent evaluation of several regional climate models suggests that changes in U.S. wind resources through the middle of the century will not exceed changes associated with historic variability. Solar energy. Increasing temperatures could reduce potential generation capacity of solar PV. Annual and seasonal photovoltaic PV output could be affected by increases in ambient air temperature, changes in cloud cover, and changes in haze, humidity, and dust. However, limited information has been published on the potential impacts of higher temperatures on solar resources in the United States. Increasing temperatures decrease the efficiency of PV systems. The extent to which PV efficiencies are affected by temperature depends on the semiconducting material used. Crystalline silicon PV cells are more susceptible to heat-related efficiency losses compared to newer technologies such as thin film PVs, which do not rely on crystalline silicon to produce electricity. The conversion efficiency of a crystalline silicon PV cell decreases by about 0.08% per 1.8 degrees Fahrenheit, 1 degree centigrade increase in air temperature when the ambient air temperature is above 77 degrees Fahrenheit. Studies of the potential change in irradiance are not consistent in either direction. Although the magnitude of the change could be as high as 15% or 20% at very high latitudes, the change would be smaller in most regions. One study suggests that solar potential will generally decrease, with the most notable decreases being in the western United States in the fall, winter, and spring. In most of the United States, this study projects a trend toward decreased seasonal mean daily global radiation in the range of 0% to 20% by mid-century. One study in Europe estimated that a 2% decline in solar radiation paired with a 6.7 degree Fahrenheit, 3.7 degrees centigrade increase in average ambient temperature could decrease solar panel power output by 6%. Understanding how cloud cover changes, including the types of clouds, will be important for understanding future solar resource potential. For example, increases in high, thin cirrus clouds that are highly transparent to solar radiation will not have the same impact as lower clouds such as stratocumulus clouds that are not as transparent and will result in less solar energy reaching the Earth's surface. Electric grid. The U.S. electric grid is a large and complex system that consists of more than 9,200 electric generating units with more than 1,000 gigawatts of generating capacity connected to more than 300,000 miles of transmission lines. Increasing temperatures are expected to increase transmission losses, reduce current carrying capacity, increase stresses on the distribution system, and decrease substation efficiency and lifespan. Increasing temperatures reduce transmission system efficiency and could reduce available transmission capacity. Approximately 7% of power is lost in transmission and distribution, and these losses increase as temperatures increase. In addition, as temperatures increase, the current carrying capacity of electricity lines decreases. For example, one study of the California power grid projected that during the hot periods of August in 2100, under a higher emissions scenario, a 9 Fahrenheit, 5 centigrade increase in air temperature could decrease transmission line capacity by 7 to 8%. The same study projects that 9 Fahrenheit, 5 centigrade warming in 2100 could cause substation capacity to fall by 2 to 4%. However, these capacity losses could be reduced by modifying future operating practices and system designs. The effects of high temperatures may be exacerbated when wind speeds are low or nighttime temperatures are high, preventing transmission lines from cooling. This is a particular concern because nighttime temperatures have been increasing at a faster rate than daytime temperatures, and they are projected to continue to increase. System transmission losses during a heat wave could be significant and contribute to electric power interruptions and power outages. During a 2006 heat wave, electric power transformers failed in Missouri and New York, causing interruptions of the electric power supply. In addition, more than 2,000 distribution line transformers in California failed during a July 2006 heat wave, causing loss of power to approximately 1.3 million customers. Increasing temperatures can also cause sag of overhead transmission lines due to thermal expansion. A relatively small increase in thermal expansion can produce a significant increase in sag. This initial sag increases with line temperature because the conducting material of which the line is made expands as line temperature increases, effectively lengthening the line. This can pose many risks, including fire and safety hazards, and increased chance of power outages due to lines contacting trees or the ground. Replacing or retrofitting transmission lines can be expensive and may include reducing the distance between transmission towers or increasing tower heights. More frequent and severe wildfires increase the risk of physical damage to electricity transmission infrastructure and could decrease available transmission capacity. Increasing temperatures and drought could exacerbate the risk of wildfire, which poses a risk to electricity transmission. Wildfires can cause physical damage to wooden transmission line poles, and the associated heat, smoke, and particulate matter can also impact the capacity of a transmission line. Soot can accumulate on the insulators and attach transmission lines to towers, causing leakage currents, and ionized air in the smoke could act as a conductor, causing arcing between lines. Either of these can cause an outage. In addition, fire retardant used in firefighting can foul transmission lines. The probability of exposure to wildfires for some lines in California is projected to increase by 40% at the end of the century. Wildfire impacts on electricity transmission and distribution. In 2007, the California Independent System Operator Corporation, CAISO, declared an emergency when, in 2 days, one wildfire caused the Southwest PowerLink transmission system to go out of service, and another fire caused 2 additional high-voltage transmission lines to trip offline. CAISO asked San Diego Gas and Electric and Southern California Edison to reduce electric load by a total of 500 megawatts, and also requested voluntary energy conservation in San Diego. Over the course of the week, the fires knocked more than 24 transmission lines out of service, and only one 230 kilovolt transmission line was serving San Diego. Estimates indicate that more than 1,500 utility poles were burned, more than 35 miles of wire were damaged, and nearly 80,000 customers in San Diego lost power. Energy demand. As temperatures increase, energy demand for heating is projected to decrease, while energy demand for cooling is projected to increase. However, the impacts of higher temperatures on net delivered energy and primary energy consumption are uncertain. In addition, as temperatures increase, annual electricity demand for cooling is projected to increase. Increasing temperatures will likely increase electricity demand for cooling and decrease fuel, oil, and natural gas demand for heating. Many factors can affect energy demand, including temperature and other weather conditions, population, economic conditions, energy prices, consumer behavior, conservation programs, and the characteristics of energy-using equipment. While the effects of rising temperatures on overall energy demand are difficult to estimate, it is expected that where cooling, largely from electricity, accounts for the largest share of energy use in residential, commercial, and industrial buildings, such as in southern states, increases in cooling will exceed declines in heating from a combination of natural gas, fuel oil, and electricity, with net energy use in buildings in such regions expected to increase. In contrast, for northern states, where energy demand for heating currently dominates, there could be a net reduction in energy demand. However, climate-induced switching from heating to cooling may contribute to increased primary energy demand, even if site energy demand declines, since primary energy demand includes losses in generation, transmission, and distribution that are greater for cooling. Energy demand is often estimated as a function of heating degree days, HDDs, and cooling degree days, CDDs. HDDs and CDDs measure the sum of the daily variation of temperature below or above a reference temperature. By the end of the century, the number of CDDs for these 4 cities is projected to increase by approximately 55%, and the number of HDDs is projected to fall by approximately 20% under a lower emissions scenario. For a northern city such as Chicago, the reduction in HDDs is projected to exceed the increase in CDDs, whereas for a southern city such as Dallas, The increase in CDDs is projected to exceed the reduction in HDDs. Changes in HDDs and CDDs change the demand for heating and cooling services, respectively. For example, many regions of the United States have market saturation of air conditioning in excess of 90%, yet there remain a large number of regions where moderate increases in temperature could further increase market penetration of air conditioning. Such increases in market penetration of air conditioning and greater use of existing air conditioning, for example, longer air conditioning season and increased use during warmer nights, will both contribute to increased demand for energy services and, consequently, increased final and primary demand, all else being equal. However, increases in the energy efficiency of air conditioning can reduce the extent to which increased demand for cooling services translates into increases in energy use. Studies suggest that the overall effect of the change in HDDs and CDDs is likely to be a net savings in delivered energy in northern parts of the United States, those with more than 4,000 HDDs per year, for the distribution of heating and cooling degree days across the United States, and a net increase in delivered energy in southern parts of the United States. After considering the effects on energy demand for heating and cooling separately, few studies have attempted to project the change in net final energy. One recent study projects a net national increase by the end of the century of 11% in residential energy demand under a higher emissions scenario and 4.5 degrees Fahrenheit, 2.5 degrees centigrade of warming. However, it is difficult to accurately assess net change in national final energy demand due to the variety of methodologies used and different assumptions made about climate scenarios, market responsiveness to a given amount of climate change, technology characteristics, and improvements, population growth, and other factors. Even in situations where net final energy demand decreases or remains largely unchanged, primary energy demand may increase with warmer temperatures because electricity generation, transmission, and distribution are subject to significant energy losses, so increases in primary energy for cooling may exceed decreases in primary energy for heating. One study projects that primary energy use will rise 2% under a scenario in which temperatures rise 2.2 degrees Fahrenheit, 1.2 degrees centigrade. Changes in net national energy expenditures also depend on how competing effects from heating and cooling add together. On average, energy used for cooling, largely from electricity, is more expensive to the final consumer than energy used for heating from a combination of natural gas, fuel oil, and electricity. A 2008 study projects an annual increase in net energy expenditures for residential heating and cooling of about 10% by the end of this century for 4.5 degrees Fahrenheit, 2.5 degrees centigrade of warming, and significantly higher net energy expenditures under a higher warming scenario. Changes in energy expenditures. Net energy expenditures on residential and commercial heating and cooling are projected to increase by a total of $6.1 billion to $14.8 billion 2001 US dollars, depending on the temperature change scenario in a study of the 22-year period ending in 2025. Long-term net energy expenditures are estimated to be substantially greater, with residential and commercial heating and cooling projected to increase by $26 to $57 billion per year, 1990 US dollars, by 2100, depending upon the emissions scenario. Finally, electricity demand is projected to increase since demand for cooling is primarily supplied by electricity, while demand for heating is supplied by a variety of energy sources, including natural gas, heating oil, and electricity. In a scenario in which CDDs increase 20%, the electricity demand for residential air conditioning is projected to increase 20 to 60%, whereas total residential electricity consumption is projected to increase 1 to 9%. Another study projects that continued warming will increase U.S. electricity demand for air conditioning by 30% in 2030, and by nearly 100% by the end of the century. To put this in perspective, in 2011, EIA estimates that approximately 16% of total residential and commercial electricity use was for cooling. Increases in electricity demand will vary regionally and seasonally. Several studies examine changes in residential electricity demand at the state or local level and report a range of projected increases. In addition to regional variations, studies have also examined seasonal variations on electricity demand. For example, in the Pacific Northwest, the projected change in electricity demand is greater in the summer than in the winter. A 3 degrees Fahrenheit, 1.6 degrees centigrade increase in summer temperatures is projected to increase average monthly load by 1,000 megawatts, whereas a 2 degree Fahrenheit, 1.1 centigrade increase in winter temperatures is projected to decrease average monthly load by 600 megawatts. For comparison, the average monthly summer and winter loads for this region were approximately 21,000 megawatts and 24,000 megawatts, respectively, in 2007. Lastly, population growth is also expected to increase total energy demand, exacerbating the impacts on electricity demand attributed to increasing temperatures alone. For example, excluding impacts of a warming climate and considering an annual population growth rate of 0.9%, the EIA projects that U.S. electricity demand will increase by 22% between 2010 and 2035. Additional investments due to climate impacts. One study estimates that 34 gigawatts of additional generating capacity will need to be constructed in the western region alone by 2050 to reliably meet the increased peak load due to projected increasing temperatures solely from climate change, excluding capacity additions due to population changes. The costs of new generation, largely assumed to be new fossil generation, are estimated to be $45 billion in 2005 dollars. The capital investment cost to build the additional capacity is projected to be about $8.9 billion. And the net present value for additional fuel and operating and maintenance costs is about $36 billion. Increasing magnitude, frequency, and duration of extreme heat events will result in higher peak electricity demands in many regions. Higher summer temperatures will increase electricity use, causing higher summer peak loads. A 2008 study indicates that peak electricity demand in California is expected to increase linearly for temperatures above 82 degrees Fahrenheit, 28 degrees centigrade, at a rate of approximately 700 megawatts per 1 degree Fahrenheit, 0.6 degrees centigrade. However, some reports indicate that average demand increases non-linearly as temperature increases. Projected increases in peak electricity demand vary depending on the models and emissions scenarios used. In California, for example, although projections vary, there are clear trends across several studies that show increased peak electricity demand of less than 5% in the near term, prior to mid-century, and close to 20% by the end of the century. Without considering population growth, peak demand in California is projected to increase above the baseline period, 1961 to 1990, by 1% to more than 4% by 2034, depending on the climate model and warming scenario. By mid-century, peak demand is projected to increase by 2.8 to 7.7% under a lower emissions scenario, and by 3.4 to 10% under higher emissions scenarios. Evaluation of the future effects of extreme high temperatures on electricity demand in California, assuming no growth in generation capacity or population, reveals a potential for electricity deficits of as high as 17% during extreme heat events. The number of days of extreme high temperatures in California is projected to double by 2035 through 2064 as compared to 1961 to 1990. By the end of the century, the number of days of extreme high temperatures is projected to increase an average of 4 times, 5.5 times, and 6.5 times, depending on the emissions scenario. In addition, all scenario combinations indicate an increase in region-wide extreme temperature conditions of a severity associated with electricity shortages under the current configuration of the electric power system and patterns of demand, extreme heat events, and wholesale electricity prices. A sustained period of high temperatures across Texas in 2011 created sharp increases in wholesale electricity prices. In one instance, the 15-minute real-time price averaged $45 per megawatt hour in the morning, but increased to $1,937 per megawatt hour in the afternoon during peak demand. In general, the increased frequency of days with extreme heat is not the only factor contributing to peak demand. Increased population levels and economic growth will lead to increased electricity demand and could further increase the need for generation capacity. In contrast, technology advances, such as improvements in air conditioning efficiency, could help reduce the projected increases in electricity demand. In addition, because air conditioning use is greatest during the same periods of extremely high temperatures that can lead to transmission losses and reduced thermal efficiencies at electric generating facilities, increased cooling demand may increase the occurrence of peak loads coinciding with periods when generation efficiencies are lowest. Average peak capacity losses in California are projected to be 1.7 to 2.7% under a lower emissions scenario, and 2.0 to 4.6% under a higher emissions scenario by the end of the century. Other studies suggest that, as a result of increasing temperatures, peak demand could increase by 10% to 21% and up to 25% when generation losses from higher temperatures are included. End of Section 2. Recording by Patrick McAfee, Merritt Island.